So now I want to do a little exercise, and you'll notice that I've changed my layout. I'm hoping that the little thing below with the theorem will be helpful. I'll be trying things out as we go. Probably I should get one of those things that allows me to make the rest of the things disappear and just etc. But never mind. I'm learning as we progress. So what I want to do here is an example of using the SVB in another context, which was the theorem that you're seeing down there. So, well, I mean, so using the pseudo-inverse to solve a linear least squares problem using the pseudo-inverse. So the example that I want to look at is the following. So we take the matrix A equal to, I'll be watching my notes from time to time because I've got things written down on the side. And so we want this matrix A and the vector B equal to 3 and 5. Now, one thing you'll see right away from a variety of angles, let's say, is that matrix A here, it is, well, its determinant is 0, which you can see in two ways. You can think, well, you can compute it right away. It's a 2 by 2 matrix, but you can also observe that the first column is half of the second column, or the first row is half of the second row. So this means the determinant is going to be 0. And also what this means is, okay, so the theorem that tells us that the rows are linearly independent, of course, does not hold. Okay, so the rows of A here are not, well, they are linearly dependent. So the theorem that tells us that a single solution exists is not going to be applicable. Let me see if I can do this. It is not going to be applicable, but this theorem here is one that we are going to be able to use. Okay, for least squares revisited. So to solve this problem, we're going to have to compute the pseudo-inverse. And solving this problem is going to involve a variety of approaches, and you'll see it's, even though the problem is well, I mean, it's as small as they can be, it is still going to be quite involved. And I want you to get a sense of the complications that can arise when you're doing this. Okay, so let's get going. We'll be needing the pseudo-inverse, which means that we need to find an SVB for the matrix A, and we'll need to then invert D so that we have the result. So let's get going. So first of all, so let me make the remark. So the rows and columns, let's say columns because that's the way our results are formulated. Columns of A are linearly dependent. Which means that we cannot apply, we need to use, or we should, it's not as prescriptive as need, but we should use the theorem using a pseudo-inverse. Inverse. Okay, so let's get started. So we need an SVB of the matrix A. So let's get started. Matrix A transpose times A is equal to A transpose is the matrix 1, 2, 2, 4. A is the matrix 1, 2, 2, 4. You notice in passing that that matrix is symmetric. Okay, so that's why the transpose is equal to itself, to the matrix itself. So carry out this computation. I have 1 plus 4 is 5. I have 2 and 8 is 10. I have 2 and 8 is 10. And I have 4 and 16 is 20. So that is my matrix A transpose A. Now we need to compute the eigenvalues of A transpose A. And just in passing, when you're solving exercises for the assignments, this is essentially the level of detail that I would like to see. You don't have to go into enormous amounts of detail, but it is important that you tell me what you're doing. Okay, you should be able to follow what's happening, even if myself or the marker are not in your minds. So eigenvalues of A transpose A, they are solution, they are zeros, the zeros of the polynomial P of lambda, so the characteristic polynomial that I get by computing the determinant of A transpose A minus lambda times identity, and that is equal to A transpose A is this matrix here. So when I subtract lambda times identity from this, I get the matrix 5 minus lambda, 10, 10, 20 minus lambda. Okay. Let's write the factored form here at least. Well, I mean this one, 5 minus lambda, 20 minus lambda, and minus 100. Okay, so P of lambda is equal to, I said 5 minus lambda, 20 minus lambda, minus 100. Let's expand this. So we get, of course, the lambdas here and here with a minus sign become lambda squared. I then subtract minus 20 minus 5, so minus 25 lambda. And I am doing what? I am, then I get plus 100 minus 100. Okay, so this is the polynomial. So the eigenvalues, so let's factor lambda out to make it clear what's happening. We get a lambda minus 25. So eigenvalues of A transpose A are lambda equals 5 and 25, sorry, and lambda equals 0. Okay, which means in turn that the singular values of A are sigma 1 equal to 5 and sigma 2 equal to 0. Okay, So we have what we want. I'm checking as we go, but I'm not saying stupid things. I've worked out the problem before. Okay. So we have the singular values. We have one positive singular value. We have one zero singular value. So now we look for the eigenvectors of A transpose A corresponding to the eigenvalues or the singular values. So eigenvector of A transpose A corresponding to lambda equals 25, let's say. Remember, we have to do things in the same order as the decreasing values of eigenvalues. So what is the eigenvector? So that eigenvector, it's a V non-zero solution to, let's write it like this, A transpose A minus 25 is my eigenvalue, minus 25 lambda, not lambda, oops, 25 times identity times V equals the vector 0. Okay, so A transpose times A, let's write it here, A transpose times A minus 25 identity times V equals 0. That's equivalent to what is my A transpose A? Yes, so this is 5, oops, having a pen problem, 5 minus 25, this is 10, this is 10, and this is 20 minus 25 times V equals 0, and this is equivalent still to minus 20, 10, 10 minus 5 times the vector V is equal to 0. Okay, once we're there, we need to solve this equation, this system. I should point out that this is actually minus 20, 10, 10 minus 5, V1, V2, of course. This is 0, 0. This is what we want to solve, okay? So to do this, notice that the second row in the matrix on the left is just proportional to the first row. So I can make that second row equal to 0 very simply. I mean, I just multiply it by 2 and add the first row, and that becomes 0. So this is equivalent to minus 2, 1. Okay, divide the first row by 10, and second row is just 0, 0. V1, V2 equals 0, 0. So this tells me that minus 2 times V1 plus V2 equals 0. That means that in my eigenvector, this is equivalent to saying that V2 is simply minus 2 times V1. Okay, plus 2 times V1, sorry. V2 is 2V1. So an eigenvector is 1, 2. But remember that what I need is for the matrix V that is going to have the eigenvectors of A transpose A, I need this matrix to have to be orthogonal, so to have orthonormal rows and columns, and therefore I need to normalize this vector. We have, so just compute it quickly, we have the norm of the vector 1, 2 is equal to square root 5. So that means an eigenvector associated to lambda equals 25 is 1 over square root 5, 5, 1, 2 over square root 5. Okay, now let's move on to an eigenvector associated to lambda equals 0, which is our second eigenvalue. We solve, again, we want a v non-zero such that H transpose A minus lambda I, which is 0 times I, v equals 0. Okay, so that's A transpose A. I simply need to solve, i.e. A transpose A is the matrix with 5, 10, 10, 20 times V1, V2 equals 0, 0. And again, in this matrix, you can see that the second row is just 2 times the first row. So that second row is going to become 0 altogether. And the first row, I can just divide by 5. So I get 1, 2, 0, 0, V1, V2 equals 0, 0. And so this is equivalent to saying that in an eigenvector associated to lambda equals 0, we have V1 plus 2V2 equals 0, which is equivalent to saying that, which way do we want to do it? That V2 is minus a half of V1. So a tentative eigenvector, I'll call it tentative because we then need to make it into a proper orthonormal eigenvector. A tentative eigenvector is 1 and minus a half. The norm of a vector 1 minus a half is what? It's square root of 1 plus a fourth, which is 5/5, so square root of 5/4, sorry, and so that's square root of 5 over 2. So that means that eigenvector of norm 1 associated to lambda equals 0 is, so divide 1 and minus a half by square root 2, so I get 2 over square root 5, square root 5 over 2, I get 2 over square root 5 and minus 1 over square root 5. This means that now I can put things together. I get that, so the matrix V is the matrix that has the eigenvector associated to the largest eigenvalue, which was which we found here to be 1 over square root 5, 2 over square root 5. And the eigenvector associated to the second largest eigenvalue, which is the second here, 2 over square root 5 minus 1 over square root 5. I'll make this 2 a little bit nicer. So we have V. The matrix sigma is then the matrix, that one is easy to make. We have 2 eigenvectors, eigenvalues, or two singular values. One is 0, the other is non-zero. So in sigma, the matrix D is the diagonal matrix with the non-zero singular values. So this is just the scalar matrix 5, okay? Because the singular value that is non-zero is the square root of the eigenvalue that is non-zero, and that eigenvalue is 25, and therefore that is 5. And this means that sigma is simply the matrix that has 5, 0, 0, 0. Okay, and this is, okay, once you've put your matrix D together, you just need to pad the other matrix to get a matrix sigma that has the same dimension as your original matrix A. Okay, so here I need a 2 by 2 matrix, and this is the matrix that I get. You're going to see that now we run into a problem. It's not a big problem, but we are going to have a little issue when computing U. So let's do this to compute U. So I'll remind you what we do to compute U. We take for I in 1 to R, and that's important, okay, for the positive singular values, we get that ui is 1 over sigma I times a vi, okay? So let's compute this. Here R equals 1. Okay, we've got only one positive singular value. Here R is equal to 1, and so ui, u1, is equal to 1 over sigma 1, which is 5, times the solution, the effect of applying A, which is the matrix, okay, I need to go back, 1, 2, 2, 4, times vi, and vi is v1 here, and v1 is this vector we wrote at the top of the page, 1 over square root 5, 2 over square root 5. Okay. So let's carry out this this computation. What do we get? Just to make my life easy, I'm going to pull out the square root, the over square root 5 that is in the vector v1, and say that it's just coming here. Okay, so this is just a little computation trick because I don't want to be carrying square root 5s everywhere. And so what do I get? I get 1 over square root 5 square root 5. This is not a d, it's a 1 over. 1 over 5 square root 5, and then the vector is 1 plus 4 is 5. 2 plus 8 is 10, and therefore my vector is 1 over square root 5. Let me keep it as a factor in front. 1 over square root 5, 1, 2. Okay. Now there's no second vector. And we still need, let me go back here. When we're taking the singular value decomposition, remember that there exists u in mm. So this is important. Here, m equals n is equal to 2. I want a 2 by 2 matrix U. And the way I've done things here, I can only pull out one vector. So the previous example we saw, things worked well, we didn't have to worry about it. But in this particular case, this is not working, okay? Because if I take just this vector, I have a 2 by 1 matrix. It's not a 2 by 2. And I'm not going to create another vector U from using the formula here, because I can't divide by sigma I when sigma I is 0, okay? So what do I need to do? Well, U is orthogonal. So here we're going to need to apply Gram-Schmidt to make another vector that's orthogonal to the vector we just created. and that we're going to add to U to make it an orthogonal matrix. Okay, so let me go back to that result for now. So how do we do? Well, we need to apply to create a vector v2, u2, sorry, u2, that is orthogonal to u1. I use the symbol for perpendicular to denote orthogonality, but is orthogonal to u1. We can apply Gram-Schmidt. Okay, so what can we use as a tentative vector? So we have u1, let me write it. u1 is the vector, let's go back, 1 over square root 5, 2 over square root 5. So here I'm free to pick whatever I want. So to apply Gram-Schmidt, remember what I need is I need a set of linearly independent vectors, and I then apply the procedure to make them into orthogonal vectors. Well, to do that, I can pick anything I want. So pick U2 to be a linearly independent vector to u1, of course, that is convenient. Well, one obvious choice for this is if I take the vector 1, 0 or the vector 0, 1, I'm going to have something that is obviously linearly independent, because if I have just the first component, there's no way to make it parallel to u1, and that's going to work easily. So pick u2 to be a linearly independent vector. Say, okay, let's take u2 equal to 1, 0. Okay, that vector is linearly independent to u1, and it turns out it's a very simple vector. And now I apply Gram-Schmidt. Okay, my first vector is obviously the one I started with. u1 is equal to, or let's say v1 to use. Okay, if you remember the notation from the theorem, let me not change this. So the theorem that told us what Gram-Schmidt is said that if I take my first vector v1 to be x1, and I take my second vector, in this case, because we have only two, to be x2 minus the projection of x1 onto the projection, sorry, of x2 onto the subspace generated, spanned by x1. So this is done by doing v1 dot x2 over v1 dot v1 times v1. Okay, so here v1 is equal to u1, and I just need to compute v2. So v2 is equal to x2 is 1, 0. Okay, this guy here. X2 is 1, 0, minus v1 is 1 over square root 5, 2 over square root 5, dot with the vector x2 divided by the norm squared of v1, which happens to be 1. Remember, that's the good thing. We've already normalized u1, so its norm is 1. So this is 1. And then I'm just multiplying by v1, which is u1. Okay, so 1 over square root 5 and 2 over square root 5. Okay, so this is 1, 0. This point here. The dot product just gives me 1 over square root 5. And I'm multiplying the vector by 1 over square root 5. So let's go to the next page. V2 is 1, 0 minus, so what did I say? 1 over square root 5 times 1 over square root 5, that's simply 1/5, and the other is 2/5. So that gives me the vector 4/5 and minus 2/5. So I need to normalize V2, and I need a vector that's parallel to V2, and that is a unit length. To simplify our life, we're going to look at V2 equal to, so it's not equivalent to what I wrote before, okay? But it's a vector in the same direction. So I'll consider V2 of this form. Okay, I can multiply by minus 5, by 5, sorry, and I still have a vector that's parallel. Or actually, I can even do better. I can take this vector. Okay, so this vector has norm square root 5. So we should consider, sorry, V2 equals to 2 over square root 5 minus 1 over square root 5. This has norm 1. It's orthogonal to V1 that we had before. And that tells us that U is equal to, where was this? Where's my U1? 1 over square root 5, 2 over square root 5. And 2 over square root 5 minus 1 over square root 5. Okay, so the SVD, an SVD of A is A equals U sigma V transpose with, it's good to summarize what you have, okay, with U equal to the matrix that we just found, which was 1 over square root 5, 2 over square root 5. Where am I? 2 over square root 5, and where was the minus sign? 2 over square root 5 minus 1 over square root 5. Sigma was simply the matrix that had 5, 0, 0, 0. And V was the matrix, where is V? 1 over square root 5, 2 over square root 5, minus 2 over square root 5, and 1 over square root 5. And I will let you check that this is indeed true. I did, and it works. So that is the solution to this problem. But now I need to get to the pseudo-inverse. So the pseudo-inverse then is, well, it's that formula that's appearing at the bottom right here. A plus is V sigma plus U transpose. V, okay, we have written here, sigma plus is the matrix, as announced below, that has D inverse and the rest 0. D is the number 5. D inverse is 1 over 5. The rest is 0. Okay, So now we can assemble that matrix A plus. And here I'm just going to give you the computed solution. It's very easy to find. Where is A plus? It is 1 over 25, 2 over 25, 2 over 25, and 4 over 25. And when you look for your solution, and thus, if I apply the theorem on the previous slide, x tilde is equal to A plus B, and that equals to, I'll write the result right away, 13 over 25, 26 over 25. Okay, and we have a solution.